Think about what exactly happens when you cook. You aren't simply following a pre-programmed list of physical motions. You think, I need milk for this recipe. You reach to the fridge, you realize you're out of milk, and you adjust your plan to use cream instead. It's a continuous, tight feedback loop. We constantly alternate between inner speech, reasoning about our goals, and external observations, acting on the messy, unpredictable world around us. Historically, large language models have been unable to replicate this. They've been designed to process a prompt and spit out an answer in one go, without the ability to pause, interact, or check their work against reality. Lacking this bridge between internal logic and the external environment, these models have remained trapped. They are brilliant text generators, but they struggle to act as autonomous problem solvers. To understand why, look at how researchers have historically built AI architectures. One approach is the model that only thinks. Techniques like chain of thought prompt an AI to write out its reasoning step by step, but it remains a closed, static system. Because it can't check the real world, a thinking-only AI often hallucinates, inventing facts based on outdated data. Once a bad assumption enters the logic chain, it cannot self-correct. The error cascades, multiplying into entirely wrong conclusions. The alternative is the model that only acts. These systems navigate environments by outputting direct commands, like clicking a button or moving a cursor, without ever forming a high-level plan. Without a working memory to track what they've already tried, these acting-only models frequently get stuck in mindless loops. They will stubbornly try to open the same empty drawer over and over. Successful task solving requires a specific synergy: internal thought to guide the action and external action to ground the thought in reality. That brings us to the ReAct architecture. It's a framework that forces a language model to generate both task-specific actions and visible reasoning traces, interleaved together. ReAct uses a thought-action-observation loop. First, the AI thinks out loud, splitting a complex goal into smaller substeps. It executes an action, and the environment returns an observation. This reality check feeds back into the thought phase, adjusting the plan. Thoughts plan the route, while actions gather the actual, current facts. This active synchronization keeps the AI from making up information or getting stuck in a rut. You can see this clearly in text-based household navigation tests. Given a prompt to find a specific object, a ReAct model starts with a thought. It reasons that the item is likely stored in the kitchen fridge. It executes the action to go to the fridge. The environment then returns an observation. The fridge door is closed. Instead of repeatedly trying to grab the item through a solid door, the model prints a new thought. It recognizes the obstacle, updates its working memory, and decides its next action must be to open the door. This is even more effective for knowledge retrieval. When tasked with answering a complex question, the model uses actions to search external databases, pulling in verified facts before it formulates an answer. For example, if asked to verify whether a specific actor worked for a certain TV network, the AI doesn't guess. It searches for the actor's Wikipedia page, reads the resulting text, and grounds its final answer in the retrieved facts. By maintaining this active working memory step by step, ReAct turns the language model into a dynamic, adaptable agent that can navigate unknown variables. When put to the test, this approach yields an absolute success rate jump of 34% in complex navigation environments compared to standard imitation learning models. Researchers achieved this without dumping massive amounts of new training data into the system. They simply restructured how the AI accesses its existing intelligence using a few careful prompts. But raw performance isn't the only benefit here. This architecture directly addresses the infamous black box problem of artificial intelligence by creating a fully transparent audit trail. Because the AI prints its inner monologue at every single step, we can read, audit, and verify the exact logic driving every decision it makes. That transparency opens the door to real-time human controllability. If an AI is halfway through a complex task and makes a logical error in its printed reasoning, a human operator can simply intervene and edit the text of the AI's thought to correct that assumption on the fly. The AI instantly reads the human's correction, updates its action plan, and proceeds to successfully complete the objective. This framework creates a more capable, autonomous problem solver while bridging the gap between human and artificial intelligence. These are agents we can finally understand, trust, and collaboratively guide.